I have some assignments that I want to give you back, and I'm just going to put them here, and I'll ask you to pick them up as soon as we take a break. There are explanations there how they were computed in red. If you have questions, you can ask me, so I can ask my grader about it. Now, I promised you that I would move on today, and that's what I'm going to do. I'm moving on to something that you're going to love. Practically, chapter 12 is integration of functions of several variables. And in that tool one, you're going to see how we introduce introduction to the double integral. But you will say, wait a minute, I don't even know if I remember the simple integral. And that's why I'm here. I want to remind you what the definite integral was. Both as a formal definition. Let's do it as a formal definition first, then come up with a geometric interpretation based on that, and finally write down the definition and the fundamental theorem of calculus. So assume you have a function that's continuous over a certain interval AB, interval in R. And you know that in that case, you can define the definite integral of f of x from or between a and b. And as a notation, it is denoted by integral from a to b f of x dx. Well, how do we define this? This is just a notation. How do we define it? We have to have a setup. And we are thinking of a xy frame. You have a function f that's continuous. And you are thinking, oh, wait a minute, I would like to be able to evaluate the area under the integral. And if you ask your teacher when you are in 4th grade, your teacher will say, well, I can give you some graphing paper. And with that graphing paper, you can eventually approximate your area like that. Sort of what you get here is like you draw the horizontal so that the little part above the horizontal cancels out with the little part below the horizontal. So more or less the pink rectangle is a good approximation of the first slice. But you say, yeah, but the first slice is a curvilinear slice. Yes, but we make it like a step function. So then you say, okay, how about this fellow? I'm going to approximate it in a similar way, and I'm going to have a bunch of rectangles on this graphing paper, and I'm going to compute their areas, and I'm going to come up with an approximation, and I'll give it to my 4th grade teacher. And that's what we did in 4th grade. But this is not 4th grade. And actually, it's very relevant to us that this has applications to our life, to our digital world, that people did not understand when Riemann introduced the Riemann sum. They thought, okay, the idea makes sense that practically we have a huge picture here, and I'm taking A and B and a function that's continuous over A and B, and And then I say I'm gonna split this into equidistant intervals. I don't know how many I want, but I will, let me make them 8 of them. I don't know, they have to have the same length. And I'll call this delta x. It has to be the same, and you guys, please forgive me for the horrible picture. They don't look like the same step, delta x, but it should be the same. In each of them, I arbitrarily, say it again, Magdalena, arbitrarily pick x1, x1 star, and another point x2 star. Wherever I want inside, I'm just very imaginative. x4 star, and this is x8 star, but let's say that in general, I don't know, they are 8, they could be n. xn star. And passing to the limit with respect to n going to infinity, what am I gonna get? Well, in the first case, I'm going up, and I'm hitting at what altitude? I'm hitting at the altitude called f of x1 star. And that's going to be the height of this, what is this strip, right? Or rectangle. Okay, and I'm going to do the same with the green for the second rectangle. I'll pick x2 star, then that doesn't work. And I'll take this, let's see if I can do the light green with the springs here. Let's see, that's beautiful. I go up, I hit here at x2 star, I get f of x2 star, and so on and so forth, until I get to, let's say, the last of the Mohicans. This will be xn minus 1, and this is going to be xn star, the purple guy. And this is going to be the height of that last of the Mohicans. So when I compute the sum, I call that approximating sum, or Riemann approximating sum, because Riemann had nothing better to do than invent it. He didn't even know that we are going to get pixels that are in larger and larger quantities, like I get 3,000 by 900. He didn't know we are going to have all those gadgets, digital gadgets. But passing to the limit practically should be easier to understand for teenagers now age, because it's like making the number of pixels larger and larger, and the pixels practically invisible. Remember, I mean, I don't know, those old TVs, color TVs where you could still see the squares? Mm-hmm. Well, yeah, when you were little. But I remember they're much better than you. And yes, as the number of pixels will increase, that means I'm taking limit and going larger and larger. That means practically limit at infinity will give me an ideal image. My eye will be as if I could see the image, that's a curved linear image, as a real person. And of course, the quality of our movies really increased a lot, and this is what I'm trying to emphasize here. So you have f of x1 star, delta x, plus the last rectangle area, f of xn star, delta x. Well, as a mathematician, I don't write it like that. How do I write it as a mathematician? Well, we are funny people. We like Greek. It's all Greek to me. So we go sum n from, k from 1 to n, f of x sub k star. So I have k from 1 to n exactly in rectangles area to add. And this is going to be delta x, which is the same everywhere. That, in that case, I made the partition is equal, so practically I have the same distance. And what is this limit? That is going to be exactly integral from a to b of f of x dx. And I make a smile here and I say I'm very happy. This is as a meaning, it's the area under the graph. If, well, I didn't say something important, want it to be positive, otherwise it's getting not to be the area under the graph. The integral will still be defined like that, but what's going to happen if I have, for example, half a bit above and half a bit below? I'm going to get this and I'm going to get that, and when I add them, I'm going to get a negative answer because this is a negative area and that's a positive area, and they try to annihilate each other, but this guy under the water is stronger, like an iceberg that's 20% on top of the water, 80% of the iceberg is under the water. So the same thing, I'm going to get a negative answer in volume or area of water. Okay, now, we remember that very well, but now we have to generalize this thingy to something else. And I will give you a curvilinear domain. Where shall I erase? I don't know. Here. What if somebody gives you the image of a potato? Well, I don't know, something, blah, blah, some nice curvilinear domain, and says, you know what? I want to approximate the area of this image, curvilinear image, to the best of my abilities, and compute it, and eventually I have some weighted sum of that. So if one would have to compute the area, it wouldn't be so hard, because we would say, okay, I have to partition this domain into small sections using a rectangular partition or square partition. Rectangular partition. And how? Well, you have to imagine that I have a grid, and I'm partitioning the whole thing. And you say, wait a minute, it's not so easy. I mean, they are not all the same area, Magdalena. Even if you try to make these equidistant in both directions, look at this guy, look at that guy, he's much bigger than that. Look at this small guy, and so on. So we have to imagine that we look at the so-called norm of the partition, and let's say the norm or the length of the partition is denoted like that. We have to give that a meaning. Well, let's say this is the highest diameter for all subdomains. Not subdomains, subdomains in the picture. And you say, wait a minute, but these subdomains should have names. Well, they don't have names, but assume they have areas. This would be, I have to find a way to denote them and be orderly. A1, A2, A3, A4, A5, AN, stuff like that. So practically I'm looking at the highest diameter. When I have a domain, I look at the largest distance inside that domain. So what would be the diameter? The largest distance between 2 points in that domain, I'll call that the diameter. Okay, I want that diameter to go to 0 in the limit. So I want this partition to go to 0 in the limit, and that means I'm shrinking the pixels. Shrinking in quotes the pixels. Okay, how would I mimic what I did here? Well, it would be easier to get the area in this case. I would have some sort of the curvilinear area of the domain. Let's call it, what do you want to call it? D from domain. Inside the domain, okay? This whole thing would be what? Would be limit of summation of, let's say, limit of what kind? K from 1 to n. Limit n goes to infinity. K from 1 to n. Of these tiny a sub k's, areas of the subdomain. Wait a minute, but you say, but what if I want something else, like I'm going to build some geography. This is the domain, that's something like on a map, and I'm going to build a mountain on top of it. I'll take some Play-Doh, and I'm going to model some geography. And you say, wait a minute, do you make mountains? I'm afraid to make rocky mountains because they may have points where the function is not smooth. If I don't have derivative at the peak, then I'm in trouble, in general. Although you say, well, but the function has to be only continuous. I know, but I don't want any kind of really nasty singularity where I can have a crack in the mountain or a well or something like that. So I assume the geography to be smooth, the function above is continuous, and the picture should look something like, let's see if I can do that. The projection, the shadow of this geography would be the domain D. And this is Z equals f of xy. You say, what, Magdalene? I don't understand. The exact shadow of this fellow where I have the sun on top here, that's the sun. Spring is coming. The shade is the planar domain xy. I take all my points in xy. I take really all my points in xy, and the value of the altitude on this geography at the point xy would be z equals f of xy. And somebody's asking me, okay, if this would be a can of Coke, it would be easy to compute the volume, right? Practically, you have a constant altitude everywhere, and you have the area of the base times the height, and that's your volume. But what if somebody asks you to find the volume under the hat? Find the volume under this graph.
I'll take apart of two functions. So the top line will be the one function, and the bottom line will be another function. So take the volume of the top function minus the volume of the bottom function, and it'll give me the total volume of the object.
And actually, I want the total volume above the sea level. So I'm gonna, sometimes I can take it up to a certain level where, let's say, the mountain is up to here, and I want it only up to here. But if I want everything, including the walls could be cylindrical. If I want all the volume, that's gonna be a little bit easier. Let's see why. I will have limit. The idea is that, as you said very well, limit n goes to infinity, a sum k from 1 to n. And what kind of partition can I build? I'll take the line, and I'll say I'll build myself a partition with, let's say, the typical domain AK. I have A1, A2, A3, A4, AK, AN. How many of those little domains? AN. That will be all the little subdomains inside the green curve, the green loop. In that case, what do I do? For each of these guys, I go up and I go, oh my God, this is like, looks like skyscraper, but the corners, when I go through the surface, are in that different dimensions. What am I gonna do? That forces me to build a skyscraper by thinking I take a point in the domain, I go up until that hits the surface, pinches the surface, and this is the altitude that I'm gonna select for my skyscraper. And here I'm gonna have another skyscraper, and here another one and another one. So practically it's dense. I have a skyscraper next to the other, more or less like it is in NYC. Not so many gaps in certain areas. So I'm gonna say f of x kappa star, those will be the altitudes of the buildings. Magdalena, you don't know how to spell. Altitudes of the buildings. These are, what are they? Parallelepipeds. Can you say parallelepiped? Okay, times what? AK, where AK will be the basis of the area of the basis of a building. Okay, the green part would be the flat area of the floor of the skyscraper. Is this hard? Gosh, yes. If you were to do it by hand and take the limit, you would really kill yourself in the process. This is how you introduce it. You can prove this limit exists, and you can prove that limits exist and will be the volume of the region under the geography z equals f of xy and above the sea level. The sea level meaning z equals 0. Yes,
what does it say under A or K?
AK.
No, what does it say under it? The
Volume of the region under.
Oh no, like right under it, like
Here?
no, up.
Here?
Yes.
Area of the basis of a building.
the basis.
So practically this green thingy is a basis of the basement. How large is the basement of that building? AK. Now, how am I going to write this? This is something new. We have to invent a notion for it. And since it's AK looks like more or less like a square of a rectangle, you think, well, okay, if it's a rectangle, I know I'm going to get delta x times delta y, right? The width times the height, whatever those two dimensions. It makes sense, but what if I have this domain that's curvilinear, or that domain, or that domain? Of course, the diameter of such a domain is less than the diameter of the partition, so I'm very happy. The highest diameter, say I can get it here, and this is still shrinking to 0 when the pixels are shrinking to 0. But what am I going to do about those guys? Well, you can assume that I am still approximating with some squares, and as the pixels are getting to be many, many, many more, it doesn't matter that I'm doing this. Let me show you what I'm doing. So on the floor, this is the city floor, whatever it is. What we do in practice, we approximate that like on the graphing paper with tiny square domains, and we call them delta AK will be delta XK times delta YK. And I try to make it a uniform partition as much as I can. Now, As the number of pixels goes to infinity and those pixels will become smaller and smaller, it doesn't matter that the actual contour of your Riemann sum will look like graphing paper. It will get refined, more refined, more refined, smoother and smoother, and it's gonna be really close to the ideal image, which is a curve. So as that n goes to infinity, you're not gonna see this, what is this called, zigzag thingy. Not anymore. The zigzag thing, you will go into the limit to the green curve. And this is what the pixels are about. And this is how our life changed a lot. Okay? All right. Now, good. How am I going to compute this thing? Well, I don't know. But let me give it a name first. It's going to be double integral over, what do you want the floor to be called? We called D domain before. What shall I call this? Big D. Not round D. Over D. That's the floor, the foundation of the whole city, of the whole area of the city that I'm looking at. Then I have f of xy, dA, and what is this? This is exactly that. It's the limit of sum of f. What is the difference here? You say, wait a minute, Magdalena, but I think I don't understand what you did. You tried to copy the concept from here, but you forgot you have a function of two variables. In that case, this Mr. whoever it is that goes up is not xk, it's xkyk. So I have two variables. Doesn't change anything, it's still a couple. This couple represents a point on the skyscraper, so that when I go up, I hit the roof with this exact altitude. So what is double integral of a continuous function f of x and y, two variables, with respect to area element? Well, it's going to be just the limit of this huge thing. In practice, how do we compute it? Let's see how we compute it in practice. It shouldn't be a big deal. What if I have a rectangular domain? And that's going to make my life easier. I'm going to have a rectangular domain in plane. And which one is the x-axis? This one. From A to B, I have the x moving between A and B. And Mr. Y says I'm going to be between C and D. C is here and D is here. So this is going to be the so-called rectangle AB cross CD, meaning the set of all the pairs or the couples xy inside it. What does it mean? Xy in plane with the property that x is between A and B, thank God, it's easy, and y must be between C and D, also easy. A, B, C, D are fixed real numbers in this order. A is less than B, C is less than B. And we have this geography on top. And I will tell you what it looks like. I'm going to try and draw some beautiful geography. And now I'm thinking of my son who is 10. He played with this kind of toy that was exactly this color, lime, and it had needles. Do you guys remember that toy? I'm sure you're young enough to remember that. You have your palm like that, and you see this square thingy, and it's all made of needles that look like thin, tiny skyscrapers. And you push through, and all those needles go up and take the shape of your hand. And of course, he would put it on his face, and you could see his face, and so on. But what is that? That's exactly a Riemann sum, a Riemann approximation, because if you think of all those needles or tiny, what are they, like tiny skyscrapers, the sum of them approximates the curvilinear shape. If you put that over your face is nice and smooth, curvilinear except for a few singularities. But if you actually look at that needle thingy that is giving the figure, you recognize the figure. It's like a pattern recognition, but it's not your face. I mean, it is and it's not. It's an approximation of your face, a very rough face. You have to take that rough model of your face and smoothen it out. How? By passing to the limit. Okay? And this is what animation is doing actually. There are, on top of that, you want this to have some other properties, illumination of some sort, light coming from what angle. That is all, rendering techniques are actually applied mathematics. In animation, the people who programmed Toy Story, that was a long time ago, but everything that came after Toy Story 2 was based on mathematical rendering techniques, everything based on the notion of limit. All right. So the way we compute this in practice is going to be very simple because you're going to think, how am I going to do the rectangle? For the rectangle, it's going to be very easy. I split the rectangle perfectly into other tiny rectangles. Every rectangle will have the same dimension, delta x and delta y. Does it make sense? So practically when I go to the limit, I have summation f of xk star, yk star inside the delta x, delta y, delta Magdalena, the same kind of displacement. When I take k from 1 to n and I pass to the limit, according to the partition, what's going to happen? These guys, according to Mr. Leibniz, will go to the infinitesimal elements dx dy. This whole thing will go to double integral of f of x and y. And Mr. Y says, okay, it's like you are integrating one at a time. This is actually something that we are going to see in a second and verify it. X goes between A and B, and Y goes between C and D. And this is an application of a big theorem called Fubini's theorem that says, wait a minute, if you do it like this over a rectangle AB cross CD, your double integral can be written as three things. Double integral over your square domain f of x, y, dA, or integral from C to D, integral from A to B, f of x, y, dx, dy, or you can also swap the order because you say, well, you can do the integration with respect to y first. Nobody stops you from doing that, and y has to be between what and what? C and B, thank you. And then whatever you get to integrate that with respect to x from A to B. So no matter in what order you do it, you get the same thing. Let's see an easy example, and you'll say, start with some trivial example, Magdalena, because we are just stuck. And that's exactly what I'm going to do. I will just misbehave. I'm not going to go by the book. And I will say I'm going by whatever I want to go. X is between 0, 2, and y is between 0 and 2, and 3. This is 2 and this is 3. And my domain will be the rectangle 0, 2 times 0, 3. This is D on the floor. Compute the volume of the box of basis D and height 5. Can I draw that? It gets out of the picture. No, I'm just kidding. This is 5, and that's sort of the box. And you say, wait a minute, I know that from 3rd grade. I mean, 1st grade, whenever. How do we do that? We go 2 units times 3 units. That's going to be 6 square inches on the bottom of the box, and then times 5. So the volume has to be 2 times 3 times 5, which is 30 square inches. I don't care what it is. I'm a mathematician, right? Okay, how does somebody who just learned Fubini-Tonelli's theorem do the problem? That person will say, wait a minute, now I know that the function is going to be z equals f of xy, which in this case happens to be constant. According to what you told us, the theorem you claim, I'm not giving a proof to this theorem, but there is a sketch of the proof in the book. According to this, the double integral that you have over the domain D, and this is dA, dA will be called element of area, which is also dx dy. This can be solved in 2 different ways. You take integral from, where is x going? Do you want to do it first in x or in y? Let's do, if we put dy dx, that means we integrate with respect to y first, and y goes between 0 and 3, so I have to pay attention to the limits of integration. And then x between 0 and 2, and again I have to pay attention to the limits of integration all the time. And here, who is my f? Is the altitude 5, that's constant in my case. I'm not worried about it. Let me see if I get 30. I'm just checking if this theorem was true or is just something that you cannot apply. How do you integrate 5 with respect to y? 5y, very good. So there's going to be 5y between y equals 0 down and y equals 3 up. And how much is that 5y between y equals 0 down and y equals 3 up? What number is that? 25?
125.
15.
No, you did, you are thinking ahead. So I go 5 times 3 minus 5 times 0 equals 15. So when I compute this variation of 5y between y equals 3 and y equals 0, I just plug in and make the difference. Why do I do that? This is the simplest application of the FT, fundamental theorem. The one that I did not specify in calculus. I should have specified it when I have a g function that's continuous between alpha and beta. How do we integrate with respect to x? I get the antiderivative of little g, let's call that big G, computed at the endpoints, and I make the difference. So I compute the antiderivative at an endpoint, at the other endpoint, then I'm going to make the difference. That's the same thing I do here. So 5 times 3 is 15, 5 times 0 is 0, 15 minus 0 is 50. I keep moving. Everything in the parentheses is the number 15. I copy and paste. And that should be a piece of cake. What do I get? I get 15 times x between 0 and 2. Integral of 1 is x. Integral of 1 is x with respect to x. So I get 15 times 2, which is 30. And you go, duh, didn't I tell you so? That was elementary mathematics. Yes, you were lucky you knew the volume of the box, but what if somebody gave you a curvilinear area? What if somebody gave you something quite complicated? What would you do? You have to know calculus. That's your only chance. If you don't know calculus, you are dead meat. So, I'm saying How about another problem that proves that life is complicated, but calculus is helping us a lot with that? Suppose that I have a square in the plane between, this is x and y. Do you want the square 0, 1, 0, 1, or you want minus 1 to 1, minus 1 to 1? It doesn't matter. Well, let's take minus 1 to 1 and minus 1 to 1. And I'll try and draw as well as I can, which I cannot, but it's okay. You will forgive me. This is the floor. That's if I were, it's just a little tiny square in this room plus the equivalent square in that room and that room and that room. This is the origin. Are you guys with me? So what you're looking at right now is this square foot of carpet that I have, but I have another one here and another one behind the wall and so on. So I have everything in mind. X is between minus 1 and 1. Y is between minus 1 and 1. And somebody gives you z to be a positive function, continuous function, which is x squared plus y squared. And you go, already, oh my God, I already have this kind of hard functions. It's not a hard thing to do. Let's draw that. What are we gonna get? Your favorite valley thing that goes like this. And imagine what's going to happen with this is like a vase, a vase, a vase, whatever. Inside it has this circular paraboloid. But the walls of this vase are, I cannot draw better than that. So the walls of this vase are squares. And what you have inside is the carved circular paraboloid. Now, I'm asking you, what are how do I get to the volume, find volume of the body under Z and above D, which is minus 1, 1, minus 1, 1. It's hard to draw that, right? It's hard to draw. So, what do we do? We start imagining things. Actually, when you cut with a plane that is y equals 1, you would get a parabola. And so you have, when you look at what the picture is going to look like, you're going to have parabola like this, a parabola like that, exactly the same but parallel, a parabola like this and a parabola like that. Now I started drawing better. And you say, how did you start drawing better? Well, with a little bit of practice. Where are the maxima of this thing? At the corners. Why is that? Because at the corners you get 1, 1 for both. Of course, to do the absolute extrema, minimum, maximum, we would have to go back to section 11.7 and do the thing. But practically, it's easy to see that at the corners, you have the height 2, because this is the 0.11. And the same height, 2 and 2 and 2 at every corner. That will be the maximum that you have. So you have 1, minus 1, and so on. Minus 1, 1, and minus 1, minus 1, who is behind you. Minus 1, minus 1. That goes all the way to 2. Okay, so it's hard to do an approximation with a three-dimensional model. Thank God there is calculus, so you say, integral of x squared plus y squared, as simple as that, dA over the domain D, which is minus 1, 1, minus 1, 1. How do you write it according to the theorem that I told you about, Fubini-Tonelli? Then you have integral x squared plus y squared dy dx. Doesn't matter which one I'm taking. I can do dy dx, I can do dx dy. I just have to pay attention to the endpoints. Lucky for you, the endpoints are the same. Y is between minus 1 and 1. X is between minus 1 and 1. I wouldn't have known how to compute the volume of this vase made of marble or made of whatever you want to make it unless I knew to compute this integral. Now you have to help me because it's not hard, but it's not easy either. So we need a little bit of attention. The outer person, we always start from the inside to the outside. The outer person has to be just neglected for the time being, and I focus all my attention to this integration. And when I integrate with respect to y is the variable for me. Nothing else exists for the time being, but y being a variable, x being like a constant. So when you integrate x squared plus y squared with respect to y, you have to pay attention a little bit. It's about like the same if you had 7 squared plus y squared. So this x squared is like a constant. So what do you get inside? Let's apply the fundamental theorem of calculus. X squared y, excellent, I'm very proud of you. Plus y cubed over 3, again I'm proud of you. Evaluated between y equals minus 1 down, y equals 1 up. And I will do the math later because I'm getting tired, right? Okay, now let's do the math. I don't know what I'm going to get. I get minus 1 to 1, a big bracket, and dx. And in this big bracket, I have to do the difference between two values. So I put 2 parentheses. When y equals 1, I get x squared 1. I'm not going to write that down. Plus 1 cubed over 3, 1/3. I'm done with evaluating this sausage thingy at 1. It's an expression that I evaluate. It could be a lot longer. I'm not planning to give you long expressions in the midterm because you're going to make algebra mistakes. And that's not what I want. Okay, for minus 1, what do we have? Minus x squared. What is y equals minus 1 plugged in here? Minus 1 over 3. I have to pay attention. You realize that if I mess up a sign, it's all gone. So, in this case I say, but this, I have minus minus, in minus in front of a minus is a plus, so I'm practically doubling the x squared plus 1/3 and taking it between minus 1 and 1 and just with respect to x. So you say, wait a minute, but that's easy. I've done that when I was in Calc 1. Of course, this is the nice part, that you get to a simple integral from the ones in Calc 2 or Calc 1. Let's solve this one and find out what the area will be. What do we get? Is it hard? No. Kick Mr. 2 out. He's just messing up with your life, right? Kick him out. 2 out. And then integral of x squared plus 1/3 is going to be x cubed over 3 plus x over 3. Very good. Evaluated between x equals minus 1 down, x equals 1 up. Let's see what we get. 2 times bracket. I'll put a parenthesis for the first fractions and another minus and another parenthesis. What's the first addition of fractions that I get? 1/3 plus 1/3. I'll put 2/3 because I'm lazy. Then minus what? Minus 1/3, minus 1/3, minus 2/3. And now I should be able to not beat around the bush. Tell me what the answer will be in the end. 8/3. Does that make sense? When you do that in math, you should always think. One of the famous professors from Harvard was saying one time she asked the students, how many hours of light do we have in one day, blah, blah, blah. And many students came up with 36, 37. So always make sure that the answer you get makes sense. This is part of a cube, right? It's like carved in a cube or a rectangle. Okay, now, what's the height? If this were to go up all the way to 2, it would be 2, 2, and 2. 2 times 2 times 2 equals 8. And what we got is 8/3. Now, using our imagination, it makes sense. If I got a 16, I would say, oh my God, no, what is that? Right? So I would think, does this make sense or not? Okay. Let's do one more, a similar one. Now I'm going to count on you a little bit more. I'll try.
Calculated that by just doing like a quarter and then just multiplying it by 4, because then that would just leave us with zeros. Just
You mean in that particular figure?
It was like perfectly like smacked.
Yeah. It's nice. It's a little bit related to some other problems that come from pyramids. But by the way, how can you compute the volume of a square pyramid? Suppose that you have the same problem. -1 to 1 for x and y. -1 to 1, -1 to 1. Let's say the pyramid would have the What would be the volume of such a pyramid? The height is h. For extra credit. Can you compute the volume of this pyramid? Magdalena, pyramid using double integrals. Say the height is h, and then the basis is the square minus 1, 1 minus 1, 1. I'm sure it can be done, but do you know, now I'm testing what you remember in terms of geometry, because we will deal with geometry a lot in volumes and areas. So how do you do that in general, guys?
1/3 basically.
1/3 the height times the area of the basis, which is what? 2 times 2. 2 times 2, 4. Over 3. 4/3 h. Can you prove that with calculus? That's all I'm saying for 1 point extra credit. Can you prove that with calculus? Actually, you would have to use what you learned. You can use Calc 2 as width. Do you guys remember that there were some cross-sectional areas? Like this would be made of cheese, and you come with a vertical knife and cut cross sections. They go like that, but that's awfully hard. Maybe you can do it differently with Calc 3 instead of Calc 2. Okay? Let's pick one from the book as well. Okay, so the same idea of using the Fubini-Tonelli argument and have an iterative, evaluate the following double integral over the rectangle of vertices 0, 0, write it down, 3, 0, 3, 2, and 0, 2. So on the basis you have a rectangle of vertices 0, 3, 0, 0, 0, 3, 2, and 0, 2. And then somebody tells you, find us the double integral of 2 minus y dA over R, where R represents the region, the rectangle that we talked about. This is exactly the rectangle. And the answer we should get is 6. And I'm saying on top of what we said in the book, can you give a geometric interpretation? Does this have a geometric interpretation you can think of or not? Well, first of all, what is this animal? According to the Fubini theorem, this animal will have to be, I have it over a rectangle, so assume x will be between a and b, y will be between c and d. I have to figure out who those are. 2 minus y and 2 minus y, Magdalena, not 2y. dy dx. Where is y in between? I should draw the picture for the rectangle because otherwise it's not so easy to see. I have 0, 0 here, 3, 0 here, 3, 2 over here. Shouldn't be hard. So this is going to be 0, 2. That's the y-axis and that's the x-axis. And this, let's see if we get 6. So, and what is the meaning of the 6? I'm asking you. I don't know. X should be between 0 and 3, right? Y should be between 0 and 2, right? Now you are experts in this. We've done this twice and you already know how to do it. Integral from 0 to 3. Then I did that. And that's going to be 2y minus y squared over 2 between y equals 0 down and y equals 2 up dx. That means integral from 0 to 3, bracket minus bracket, will make my life easier, dx. Now, there is no x, thank God. So, that means I'm going to have a constant minus another constant, which means I go 4 minus 4 over 2. 2, right? The other one, for 0, I get 0. I'm very happy I get 0, because in that case it's obvious that I get 2 times 3, which is 6. So I got what the book said I'm going to get. But do I have a geometric interpretation of that? I would like to see if anybody can. I'm going to give you a break in a few minutes. If anybody could think of an interpretation, geometric interpretation, what is this f of xy if I were to interpret this as a graph? Z equals f of x and y.
Minus y.
So z equals 2 minus y is a plane.
Yes. But
Right?
then you have the parabola is going down.
And how do I get to draw this plane the best? Because there are many ways to do it. I look at this wall. The y-axis is this. The z-axis is the vertical one. So I'm looking at this plane. Y plus z must be equal to 2, right? So when is y plus z equal to 2? When I am on a line in plane, I'm going to draw that line in pink because I like pink. This is y plus z equals 2. Okay. And imagine this line will be shifted by parallelism as it comes towards you on all these other parallel vertical planes that are parallel to the board. So I'm going to have an entire plane like that, and I'm going to stop here. When I'm in the plane that's called x equals 3, this is the plane called x equals 3. I have exactly this triangle, this and thing. It's in the plane that faces me. Here, I don't know if you realize that. Let me make like a house or something nice. I think I'm getting hungry. I imagine this again as being a piece of cheese. Or it looks even like a piece of cake. Could be with layers and like. Okay. So, our question is, if we didn't know calculus, but we knew how to draw this, and somebody gave you this at the GRE or whatever exam, how could you have done it without calculus? Just by cheating and pretending, I know how to do it, but you've never done a double integral in your life, and you saw, I know it's a volume. How do I get the volume? What kind of geometric body is that?
It's a triangular prism.
Yeah.
It's a triangular prism. Good. And a triangular prism has what volume formula? Base times the height. And the height has what area? Let's see. The base would be that, right?
Yeah.
And the height would be 3. Am I right or not? The height would be 3. This is the.
It's 2. Yeah.
No, it's three.
From here to here
Three.
is 3. So how much is the? How much? Okay, from here to here is 2. From here to here is how much?
The height is only, I see.
It's also 2.
It's also 2 because look at that. It's an isosceles triangle. This is 45 to 45. So this is also 2. 2, 2. That's 90 degrees, 45, 45. Okay, so the area of this shaded purple triangle, how much is that? 2. 2 times 2 over 2. 2 times 3 equals 6. I don't need calculus. In this case, I don't need calculus, but when I have those nasty curvilinear z equals f of x, y, complicated expressions, I have no choice. I have to do the double integral. But in this case, even if I didn't know how to do it, I would still get the 6. Yes, sir?
What if we just add on the exam?
Well, that's good. I will then keep it in mind. Yes. It doesn't matter to me. I have other colleagues who really care about the method and start complaining. I don't care how you get to the answer as long as you got the right answer. Let me tell you my logic. Suppose somebody hired, thinking you're a good worker and you're smart and so on. Would they care how you got to the solution of the problem as long as the problem was solved correctly? No. And actually, the elementary way is the fastest because it's just 10 seconds. You draw, you imagine, you know what it is. So your boss will want you to find the fastest way to provide the correct solution. He's not going to care how you got to that. So no matter how you do it, as long as you got the right answer, I'm going to be happy. I want to ask you to please go to page 927 in the book and read, it's only one page, That will end section 12.1. It's called an informal argument for Fubini's theorem. Practically, it's the proof of Fubini's theorem, page 927. And then I'm going to go ahead and start homework 4, if you don't mind. I'm going to go into web work and give you homework 4. And the first few problems that you are going to be expected to solve will be out of 12.1, which is really easy. I'll give you a few minutes break and we go on with 12.2. And it's very similar, you're going to like that. And then we'll go home, wherever we need to go. Okay. So you have a few minutes of a break. Pick up your extra credits. I'll call the names. Lily? Yes. Got a lot of points. And Nitish? And you'll have 2 separate ones. Nathan? Nathan? Rachel Smith, Austin, thank you. Edgar, there you are. Aaron.
Oh, no, I
You never heard of it?
Andre.
just like teaching me something. Just keep teaching me.
Or okay.
Sharon. And Casey. Casey came up with a very good idea that I will write a review sample. Did I promise that? A review sample for the meter. And so I said yes already. Karen, and Matthew, Reagan,
You got it.
Aaron. When you submit it, you submit it. I mean, yeah. And Betsa. And Lucia, and I'm done. When we erase, yes, absolutely. Now, once we go over 12.2, you will say, oh, and I understand the Fubini theorem. I didn't go over the proof of Fubini because once I cover the more general case, which is in 12.2, you are going to understand why Fubini-Tonelli works for rectangles. So, if I think of a domain that is of the following form, in the xy plane, I go x is between a and b, right? That's my favorite x. So I take the pink segment and I say, everything that happens, it's going to happen on top of this world. I have, let's say, 2 functions. To make my life easier, I'll assume both of them positive and one bigger than the other. But in case that they are not both positive, I just need f to be bigger than g for every point, and the same argument will function. This is f, continuous positive. Then g, continuous positive, but smaller in values than this one. Yes, sir.
So this is 12.2.
That we're starting?
12.2, and you are more organized than I am, and I appreciate it. So integration over non-rectangular domain. And we call this a type 1 because this is what many books are using it, in the sense that x is between two fixed endpoints, but y is between two variable endpoints. So what's going to happen to y? Y is going to take values between the bottom one, which is g of x, and the upper one, which is f of x. So this is how we define the domain that's shaded by me with black shades, vertical strips here. This is the domain. Now, you really do not need to prove that double integral over one dA over, let's call the domain D, is what? Integral between f of x minus g of x from a to b dx. And you say, what, Magdalena, what are you trying to say? Okay, let's go back and say, what if somebody would have asked you the same question in Calculus 3? Saying, guys, I have a question about the area in the shaded stripped vertical strip thing. How are we going to compute that? And you would say, oh, I have an idea. I take the area under the graph f, and I shade that in orange. And I know what that is. So you say, I know what that is. That's going to be what? Integral from a to b f of x dx. Let's call that a1, right? a1. Then you go minus the area with brown strips under G. G of x. I call that A2. A1 minus A2. We know both of these formulas from where? Calc 1, because that's where you learn about area under the graph of a curve. This is the area under the graph of a curve F. This is the area under the graph of the curve G. The black stripped area is their difference. All right, and so how much is that? I'm sorry, I put the wrong thing, AB. That's going to be integral from A to B. Now you say, wait a minute. Based on what? Based on some sort of additivity property of the integral of one variable, which says integral from A to B of f plus g. You can have f plus minus g, doesn't matter, dx. You have integral from A to bf dx plus integral from A to b g dx. Doesn't matter what. You can have a linear combination of f and g. Yes, Matthew.
So this is just for the domain.
This
So,
is
like
what you.
if you like put it, that'd be like down. So there might be another formula up here that would be like a curved surface, and this is like the bottom. So you use an integral to find the base, and then you're gonna plug that integral into the double integral.
So I'm just using a property that's called linearity of the simple integral. Meaning that if I have even a linear combination like AF plus BG, then I have not A. Let me call big A and big B. Big A F, integral of F plus big B, integral of G. You've learned that in Calc 2. I'm doing this to apply for these areas that are subtracted from one another. If I were to add, as you said, I would put something on top of that, and then it would be like a superposition of two integrals. So I have integral from A to B of f of x minus g of x dx. And I claim that this is the same as double integral of the 1 dA over the domain D. How can you write that differently? I'll tell you how you write that differently. Integral from A to B of integral from what's the bottom value of Mr. Y. So Mr. X knows what he's doing. He goes all the way from A to B. The bottom value of Y is g of x. You go from the bottom value of Y, g of x, to the upper value f of x. And then you here put 1 and dy. Is this the same thing? You say, okay, I know this one from Calc 2, but Magdalena, the one you give us is new. It's new and not new, guys. This is Fubini's theorem, but generalized to something that depends on x. So how do I do that? Integral of 1 dy, that's what? That's y measured between two values that don't depend on x. Depend only on x. G of x on the bottom, f of x on the top. So this is exactly integral from A to B. In terms of the round parenthesis, I put what is y between f of x and g of x? F of x minus g of x dx. So it is exactly the same thing from Calc 2, expressed as a double integral. All right, now this is a type 1 region that we talked about. A type 2 region is a similar region. Practically, what you have to keep in mind is they're both given here as examples, but the technique is absolutely the same. If instead of taking this picture, I would take y to move between fixed values. Like y has to be between c and d. This is my y. These are fixed values. And then give me some nice colors. This curve and that curve. Okay, I have to rotate my head, because then this is going to be x, this is going to be y, and the blue thingy has to be a function of y. X is a function of y, so how do I call that? I have x, well, whatever, equals big F of y. And here in the red one, I have x equals big G of y. And how am I going to evaluate the stripped area? Of course, stripped because I have, again, y is between c and b. And what's moving is Mr. X. And Mr. X refuses to have fixed variables. Now he goes, I move from the bottom, which is g of y, to the top, which is f of y. How am I going to write the double integral over this domain of 1 dA, where dA is dx dy, right? Who's going to tell me? Similarly, the same thinking, the same reasoning as for this one. I'm going to have the integral from what to what, of integral from what to what. Who comes first, dx or dy? Dx, very good, and dy at the end. So y will be between c and d, and x is going to be between g of y and f of y. And here's 1. How can I rewrite this integral? Very easily. Integral from c to d of the guy on top, the blue guy, f of y, minus the guy on the bottom, g of y, dy. Some people call the vertical strip method compared to the horizontal strip method, where in this kind of horizontal strip method you just have to view x as a function of y and rotate your head and apply the same reasoning as before. It's not a big deal. Just need a little bit of imagination and the result is the same. An example that's not too hard. I want to give you several examples. We have plenty of time. Now, it says we have a triangular region, and that is enclosed by lines y equals 0, y equals 2x, and x equals 1. Let's see what that means and be able to draw. It's very important to be able to draw in this chapter. If you're not, just learn how to draw. And that will give you lots of ideas on how to solve the problems. Chapter 12 is included completely on the midterm. So the midterm is on the 2nd of April. For the midterm we have chapter 10, those 3 sections, then we have chapter 11 completely, and then we have chapter 12, not completely, up to 12:36. All right, so what did I say? I had a triangular region that is obtained by intersecting the following lines. Y equals 0, x equals 1, and y equals 2x. Can I draw them and see how they intersect? It shouldn't be a big problem. This is a line that passes through the origin and has slope 2. So it should be very easy to draw. At 1, x equals 1, the y will be 2 for this line of slope 2. So I'll try to draw. Does this look double to you? So this is altitude 2. This is the point 1, 2. And that's the line y equals 2x. And that's the line y equals 0. And that's the line x equals 1. So can I shade this triangle? Yeah, I can eventually, depending on what they ask me, find the double integral of x plus y dA with respect to the area element over t being the triangle. So now I'm going to ask, did they say by what method? Unfortunately, they say do it by both methods. That means both by x integration first and then y integration and the other way around. So they ask you to change the order of the integration or to what? Switch from vertical strip method to horizontal strip method. You should get the same answer. That's a typical final exam problem. When we test you, if you are able to do this through the vertical strip or horizontal strip and change the order of integration. If I do it with the vertical strip method, who comes first? The dy or the dx? Think a little bit. When I put the Fubini-Tonelli comes dy dx or dx dy? Dy dx. So VSM, you're going to laugh. It's not written in the book. It's like the childish name vertical strip method, meaning integration with respect to y and then with respect to x. It helped my students through the last decade to remember about the vertical strips. And that's why I say something that's not used in the book, VSM. Now, I have integral from, so who is Mr. X going from 0 to 1? He's stable, he's happy, he's going between two fixed values. Y goes between the bottom line, which is 0. We are lucky. It's a really nice problem. going to y equals 2x. So it's not hard at all. And we have to integrate the function x plus y. It should be a piece of cake. Let's do this together. Because you've accumulated seniority in this type of problem. What do I put inside? What's the integral of x plus y with respect to y? Is it hard? xy plus, somebody tell me, y squared over 2 between y equals 0 on the bottom, y equals 2x on top. I have to be smart and plug in the values y, otherwise I'll never make it. So, yes sir?
Why did you took 2x as the final value? Because like you have a specified triangle.
Because y equals 2x is the expression of the upper function. The upper function is the line y equals 2x. They provided that. So from the bottom function to the upper function, the vertical strips go between two functions. All right. So when I plug in here y equals 2x, I have to pay attention to my algebra. If I forget the 2, it's all over for me. 0 point, well, not 0 point, but 10% credit. I have no idea what I will get. So I have to pay attention. 2x times x is 2x squared plus 2x all squared. Guys, keep an eye on me. 4x squared over 2. I put the first value in a pink parenthesis, and then I move on to the line parenthesis. Evaluate that 0, but that line is very lucky. I get a 0 because y equals 0 will give me 0. What am I going to get here? 2x squared plus 2x squared. Good. What's 2x squared plus 2x squared? 4x squared. So a 4 goes out, to come out. Integral from 0 to 1 x squared dx. Integral of x squared is, integral of x squared is antiderivative, x cubed over 3. And if you take it between 1 and 0, you get 1/3. 1/3 times 4 is 4/3. How are you gonna, suppose this is gonna happen on the midterm and I'm asking you to do it reversing the integration order. Then you are gonna check your own work very beautifully in the sense that you say, well, now I'm gonna see if I made a mistake in this one. What do? I erase the whole thing. And instead of vertical strips, I'm gonna put horizontal strips. And you say, well, life is a little bit hard than this in this case, because in this case I have to look at y between fixed values, y between 0 and 1. So y is between 0 and 1, 0 and 2 fixed values. And Mr. X said, I'm going between two functions of y. I don't know what those two functions of y are. I'm puzzled. You have to help Mr. X know where he's going, because his life right now is a little bit hard. So what is the function for the blue? Now it's not blue anymore. It's brown. X equals 1. So he knows what it's going to be. What is the x function for the red line that Nitish asked about? X must be y over 2. It's the same thing, but I have to express x in terms of y. So I erase, and I say x equals y over 2. Same thing. So x has to be between what and what? The bottom and the top. Well, I turn my head. The top must be x equals 1. And the bottom one is y over 2. That's the bottom one, the bottom value for x. And he's happy. Now wish me luck, because I have to get the same thing. So, integral from 0 to 2 of integral from y over 2 to 1. Changing the order of integration doesn't change the integrand, which is exactly the same function f of xy. This is the f function. Then what changes? The order of integration. So I go dx first, dy next, and stuff. I copy and paste the outer ones, and I focus my attention to the red parentheses inside, which I'm going to copy and paste here. I have to do some math very carefully. So what do I have? I have x plus y integrated with respect to x. If I rush, it's a bad thing.
So there will be x squared
X squared
over 2
over 2
plus xy.
plus xy, taken between the following. When x equals 1, I have it on top. When x equals y over 2, I have it on the bottom. Okay, this red thing, I'm a little bit too lazy. I'll copy it and paste it separately. For the upper part, is really easy to compute. What do I get? When x is 1, 1/2 plus. When x is 1, y. All right, minus integral of, when x is y over 2, I get y squared over 4 up here, over 2. So I get y squared over 8. Plus, I plug in x equals y over 2. What do I get? Y squared over 2. Is this hard? It's very easy to make an algebra mistake on such a problem. Unfortunately, I have y plus a half plus what? What is a half plus an 8? 5 over 8 with a minus y squared. So hopefully I did this right. Now I'll go, okay, integral from 0 to 2 of all this animal, y plus a half minus 5 over 8 y squared. What happens if I don't get the right answer? Then I go back and check my work because I know I'm supposed to get 4/3. That was easy. So, what is integral of this sausage, whatever it is? Y squared over 2 plus y over 2 minus 5 over 8. Oh my God. 5 over 8 y cubed over 3 between 2 up and 0 down. When I have 0 down, I plug y equals 0. It's a piece of cake, it's a 0. So what matters is what I get when I plug in the value 2 instead of y. So what do I get? 4 over 2 is a 2 plus 2 over 2 is a 1 minus 2 cubed, thank God, that's 8. 8 simplifies with 8. Minus 5/3. So I got 9/3 minus 5/3, and I did it carefully. I did a good job. I got the same thing, 4/3. So no matter which method, the vertical strip or the horizontal strip method, I get the same answer. And of course you'll always get the same answer because this is what the Fubini theorem extended to this case is telling you. It doesn't matter the order of integration. Okay. I would advise you to go through the theory in the book. They teach you more about area and volume at page 934. I'd like you to do that, to read that. And let's see what I want to do. Which one shall I pick? There are a few examples that are worth it. One of them, okay, I'll pick the one that gives people the most trouble. How about that? I take the few examples that give people the most trouble. One example that popped up on almost each and every final in the past 13 years that involves changing the order of integration So, exam type problem. On changing the order of integration. A very tricky and smart problem is the following. Evaluate integral from 0 to 1, integral from x to 1, e to the y squared dy dx. I don't know if you've seen anything like that in AP Calculus or Calc 2. Maybe you have. In which case your professor probably told you that this is nasty. And you say, in what sense is it nasty? There is no expressible antiderivative. So this cannot be expressed in terms of elementary functions explicitly. It's not that there is no antiderivative. There is an antiderivative, a whole family actually. But you cannot express them in terms of elementary functions. And actually, most functions are so bad in real world, in the real life. Now, could you compute, for example, integral from 1 to 3 of e to the t squared dt? Yes. How do you do that? With a calculator. And what do you do if you don't have one? You go to the lab over there. There is MATLAB. MATLAB will compute it for you. How does MATLAB know how to compute it if there is no way to express the antiderivative and take the absolute and take the value of the antiderivative between b and a, like in the fundamental theorem of calculus? Well, the calculator is smart, or the computer program is smart. He uses numerical analysis to approximate this type of integral. So he's fooling you. He's playing smarty pants. He's smarter than you at this point. Okay, so you cannot do this by hand, so this order of integration is fruitless. Fruitless. And there are people who tried to do this on the final. Of course, they didn't get anywhere because they couldn't integrate it. The whole idea to this one is to, some professors are so mean they don't even tell you, hint, change the order of integration because it may work the other way around. They just give it to you and then people can spend an hour and they don't get anywhere. If you want to be mean to a student, that's what you do. So I will tell you that one is to change the order of integration for this. This is the function, you pick the function. But let's see what happens if you draw. The domain will be x between 0 and 1. This is your x value. Y will be between x and 1. So it's like you have a square. Y equals x is your diagonal of the square. And you go from, more colors please. You go from y equals x on the bottom and y equals 1 on top. And so the domain is this beautiful triangle that I made all in line. With vertical strips, this is what it means, vertical strips. But if I do horizontal strips, I have to change the color, blue. And for horizontal strips, I'm going to have a different problem. Integral dx dy. And I just hope to God that what I'm going to get is doable. Because if not, then I'm in trouble. So, help me on this one. If y is between what and what? It's a square. It's a square, so this is the same as 0 to 1, right?
Yep.
But Mr. X, how about Mr. X?
And then it will be between 1 and y.
Between Mr. X is this guy. And he doesn't go between 1, he goes between the sea level which is x equals 0,
Then,
to x equals y,
yeah.
right? So from x equals 0 to x equals y. And you have the same individual e to the y squared that before went on your nerves. Now, he's not so bad, actually. Why is he not so bad? Look what happens in the first parenthesis. This is so beautiful that it's something you didn't even hope for. So we copy and paste integral from 0 to 1 dy. These guys stay outside and they wait. Inside is our business what we do. So Mr. X is independent from e to the y squared. So e to the y squared pulls out, he's a constant. And you have integral of 1 dx between 0 and y. How much is that? 1 x between x equals 0 and x equals y. So is y. So I'm being silly, so I should have said y. Now, if your professor would have given you in Calc 2 this, how would you have done it?
U substitution.
U substitution, excellent. What kind of U substitution am I done?
Y squared equals U.
Y squared equals U, du equals 2y dy. So y dy together, they stick together. They stick together, they attract each other as magnets. So y dy is going to be 1/2 du, 1/2 pulls out, integral e to the u du. Attention, when y is moving between 0 and 1, u is moving also between 0 and 1. So it really should be a piece of cake. Are you guys with me? Do you understand what I did? Do you understand the word coming out of my mouth? It's easy. Okay, good. So what is the integral of e to the u du? E to the u. Between 1 up and 0 down. So e to the u be e to the 1 minus e to the 0 over 2. That is e minus 1 over 2. I could not have solved this if I tried it by integration with y first and then x. The only way I could have done this is by changing the order of integration. So, how many times have I seen this in the past 12 years on the finals? At least 6 times. It's a problem that could be a little bit hard if the student has never seen it before and doesn't know what to do to the problem. Let's do a few more in the same category.
Professor,
Yes.
where did this graph come from? Were we just saying it was with the same?
Okay, I read it from here. So this and that are the key. This is telling me x is between 0 and 1, and at the same time y is between x and 1. And when I read this information on the graph, I say, well, x is between 0 and 1, Mr. Y has the freedom to go between the first bisector, which is that, and the cap, his cap, y equals 1. So that's how I got to the line strips. And from the line strips I said, but I need horizontal strips. So I changed the color, and I said the blue strips go between x will be x equals 0 and x equals y. And then y between 0 and 1, just the same. It's a little bit tricky. That's why I want to do 1 or 2 more problems like that, because I know that I remember 20-something years ago, I myself needed a little bit of time understanding the meaning of reversing the order of integration.
Does it matter which way you put it?
In this case, it's important that you do reverse. But in general, it's doable both ways. I mean, in the other problems I'm going to give you today, you should be able to do either way. So I'm looking for a problem that you could eventually do another one that you could do. Nah, we don't have so many. I'm going to go ahead and look into the problem. Yeah. So it says you have this integral from 0 to 4 of integral from x squared to 4y dy dx. Draw, compute, and also compute with reversing the order of integration to check your work. When I say that, it sounds horrible, but in reality, the more you work like that one, the more familiar you're gonna feel. So what did I just say? Problem number 26. You have integral from 0 to 4, integral from x squared to 4x, dy dx. Interpret geometrically, whatever that means, and then compute the integral in two ways. With this given order of integration, which is what kind of strips, guys? Vertical strips. Or reversing the order of integration and check that the answer is the same, just to check your work.
So
First you draw, because if you don't draw, you don't understand what the problem is about. And you say, wait a minute, but couldn't I go ahead and do it without drawing? Yeah, but you're not going to get too far. So let's see what kind of problem you have. Y and x. Y equals x squared is a what? It's a parabola. And this parabola should be nice and sassy. Is it fat enough? I think it is. And the other one will be 4x. Y equals 4x. What does that look like? Looks like a line passing through the origin that has slope 4, so the slope is really high.
just straight.
Y equals 4x versus y equals x squared. Now, do they meet?
Yes.
It's exactly where do they meet? Exactly here. So 4x equals x squared. Where do they meet? Where they meet at. It has two possible roots. One is x equals 0, which is here. And one is x equals 4, which is here. So really, my graph looks just the way it should look. Only my parabola is a little bit too fat over there. So I have 0. Well, this is the point of coordinates 4 and 16. Are you guys with me? And Mr. X is moving between 0 and 4. This is the maximum level X can get. And where he stops here at 4, a miracle happens. The two curves intersect each other. Exactly at that point. So this looks like a leaf. No, a leaf ate a slice of orange. Oh my God. I don't know. I'm already hungry. So I cannot wait to get out of here. Okay, I bet you're hungry as well. Let's do this problem both ways and then we go or to have something to do. How are you going to advise me to solve it first? It's already set up to be solved, so it's vertical strips. And I will say integral from 0 to 4, copy and paste the outer part, take the inner part, and do the inner part because it's easy. And if it's easy, you tell me how I'm going to do it. Integral of 1 dy is y. Y measured at 4x is 4x, and y measured at x squared is x squared. Oh, thank God, this is so beautiful, it's so easy to do it. Let's integrate together. 4 x squared over 2 minus x cubed over 3 between x equals 0 down and x equals 4 up. What do I get? I get 4 cubed over 2 minus 4 cubed over 3. This 4 cubed is an obsession, kick him out. 1/2 minus 1/3. How much is 1/2 minus 1/3? My son knows that. Okay, 1/6, there. So we simply take it, we can leave it like that. If you leave it like that on the exam, I don't mind at all. But you can always put 64 over 6 and simplify it. Are you guys with me? You can simplify it and get what? 32 over 3. Don't give me decimals, I'm not impressed. You're not supposed to use the calculator, you're supposed to leave this in the exact fraction form like that, irreducible. Let's do it the other way around, and that will be the last thing we do. The other way around means I'll take another color, I'll do the horizontal stripes, and I will have to rewrite the meaning of these two branches of functions with x expressed in terms of y. That's the only thing I need to do, right? So, what is this? If y is x squared, what is x? The inverse function. X will be root of y. You said very well, Nitish. So I have to write, in line I have what I need to have for the line horizontal strip method. And then for the other one, x is going to be y over 4. So what do I do? So integral, one that was here hidden, but I'll put it because that's the integral. And then I go dx dy. All I have to care about is the endpoints of the integration. Now pay attention a little bit because Mr. Y is not between 0 and 4. I've had very good students under stress in the final putting 0 and 4. Don't do that. So pay attention to the limits of integration. What are the limits? 0 and 16. Very good. And x will be between root y. Well, which one is on top, which one is on the bottom? Because if I move my head, I'll say that's on top and that's on the bottom.
The right side is always on top.
So the one that goes higher is this one. This is more than that in this frame. So square root y is on top and y over 4 is on the bottom. I should get the same answer. If I don't, then I'm in trouble. So what do I get? Integral from 0 to 16. Tonight, when I go home, I'm going to hook up the homework for 12.1 and 12.2 at least. I'll put some problems similar to that because I want to emphasize the same type of problem in at least 2 or 3 applications for the homework, for the midterm, and maybe one like that will be on the final as well. It's very important for you to understand how, for this kind of domain, you reverse the order of integration. Who's helping me here? Root y. What is root y when, okay? Y to the 1/2. I need to integrate, so I need it minus y over 4. And dy. Can you help me? Integrate? 2/3 y to the 3/2 minus y squared over 8, y equals 0 on the bottom, piece of cake. That will give me 0. I'm so happy. And y equals 16 on top. So, for 16 I have 2/3 times, who's telling me what else? 64, 4 cubed. I can leave it 4 cubed if I wanted to. Minus another. Well, here I have attention, right? So I have a 16 here. I got square root of 16, which is 4 cubed. Here I put minus 4 squared, which was there, squared. How do you want me to do this
Say minus
simplification?
32.
I can do 4 to the 4. Are you guys with me? Yeah. Oh, okay, I can put, like you prefer, 16 squared. Over 8. Is it the same answer? I don't know, let's see. This is really 4 to the 4. So I have 4 times 4 cubed.
Yep.
4 cubed gets out. And I have 2/3 minus 1/2. And how much is that? Again, 1 over 6. Are you guys with me? 1 over 6. So again, I get 4 cubed over 6. So I'm done. 4 cubed over 6 equals 32 over 3. I am happy that I checked my work through 2 different methods. I got the same answer. Okay? All right, now, let me tell you something. There were also times when on the midterm or on the final, due to lack of time and everything, we put the following kind of problem. Without solving this integral, without solving, indicate the corresponding integral with the order reversed. So all you have to do, don't do that, just from here write this and stop. Don't waste your time. If you do the whole thing, it's going to take you 10 minutes, 15 minutes. If you do just the reversing of the order integration, I don't know what it takes, 1.5 minutes, 2 minutes. So in order to save time, at times we gave you just don't solve the problem, reverse the order integration. Okay. One last one. Okay, one last one. But I don't want to finish it. I want to give you the answer at home, or maybe you can finish it. It should be shorter. You have a circular paraboloid, but only the first quadrant. So x is positive. I don't know, I have to find it. Find the volume, example 4, page 934. Find the volume of the solid bounded above, this is a little tricky, by the plane z equals y, and below in the xy plane by the part of the disk in the first quadrant. So z equals y means this is your f of x and y, guys. So they gave it to you. But then they say, but also in the xy plane, you have to have the part of the disk in the first quadrant. And this is not so easy. They draw it for you to make your life easier. The first quadrant is that. How do you write the unit circle? X squared plus y squared equals 1. X squared plus y squared less than equal to 1, and x and y are both positive. This is the first quadrant. How do you compute? So they say compute the volume, and I say just set up the volume, forget about computing it. I could put it in the midterm just like that. Say set up an integral without solving it that indicates the volume under z was f of xy. That's the geography of z. And above a certain domain in plane, above D. So you have, okay, what did she teach you? She taught you that double integral over d f of xy dA can be solved. Do y has to be solved? No. Why? Because you can finish it later, you can finish it at home, or maybe I don't even want you to complete. I'm sorry, on the final, okay? So how do we do that? F is y. Would I be able to choose whichever order integration I want? It shouldn't matter which order, it should be more or less the same. What if I do dy dx? Then I have to do the Fubini, but it's not a rectangular domain. So Magdalena, be a little bit careful because this is gonna be two finite numbers, but these are functions.
There will be an x function.
So the x is between 0 and 1, and that's gonna be easy. You do vertical strips. That's a piece of cake. But if you do the vertical strips, you have to pay attention to the endpoints for y. And 1 is easy. Which one is trivial?
0.
The bottom one, 0. The one that's non-trivial is the upper one.
And there will be 1 minus
Square root of 1.
Very good. Square root of 1 minus y squared. Okay? So if I were to go one more step further without solving this, I'm going to ask you, could this be solved by hand? Well, when I have, so you have it in the book, it's,
Professor, should be at root 1 minus x squared.
oh yeah, 1 minus x squared, excuse me. Didn't I write it? Yeah, here I should have written y equals square root of 1 minus x squared. Okay, so when you do it, you go, thank you so much, you go integrate, and you have y squared over 2, and you evaluate between y equals 0 and y equals square root 1 minus x squared, and then you do the rest. In the book, they do it differently. They do it with respect to the x and the y integration. But it doesn't matter how you do it, you should get the same answer. Okay? All right? Is it hard? No.
If you keep it in that way, doesn't the square root work out better? Because there's already a y
In
there.
the other case, in the
Doing dy dx. Dx.
yeah, in the other way, it works a little bit differently. You can do a use substitution, I think. So if you do it the other way, will be what? Integral from 0 to 1, integral from 0 to square root of 1 minus y squared, y dx dy. And what do you do in this case? You have integral from 0 to 1. Integral of y dx is going to be y is a constant, x between the two values will be simply 1 minus y squared dy. So you're right, Matthew saw that because he's a prophet and he could see two steps ahead. Okay, this is very nice what you observed. What do? You take a u substitution when you go home. You get u equals 1 minus y squared, du will be minus 2y dy, and you go on. It's easy. So in the book, we got a third. If you continue with this method, I think it's the simplest.
Yeah, I got 1/3.
You got 1/3. So, sounds good. We will stop here. You will get homework. How long shall I leave that homework on? Because I'm thinking maybe another month, but please don't procrastinate. So let's say until the end of March, and keep in mind that we have included a 1 week of spring break leave, which you can use whatever, you can do whatever you want with. And some of you may be in Florida, swimming and working on a 10, and not working on homework. So no matter how, plan ahead and go to the job. 31st of March, I'm guessing. Okay, for the whole chapter.